Chapter 18 is on nuclear chemistry. 18 section 1 begins by talking about nuclear stability and just defining some terms. Nucleons refer to protons and neutrons, or any particle that are in the nucleus of an atom. And then when they're referring to nuclides, they are any combination of protons or neutrons in a nucleus. So you could have isotopes or isobars. An isotope means that you've got the same number of atoms but different, or excuse me, the same atomic number, but different mass numbers. So the protons are the same, but the neutrons are different. And then an isobar means that they have the same mass, but different atomic numbers. Binding forces, one of the main ones is called a strong nuclear force, which we've mentioned before. It's basically the attraction that's going to hold the nuclear particles together. So though protons will want to repel one another, those repulsive forces can be overcome when they're at very close distance. In larger nuclei, the strong force can't reach far enough to attract each nucleon to all the others. And when there's an imbalance between the strong force and the repulsive forces, the nucleus will start to decay. Mass defect is the mass that's converted to energy when a nucleus forms. Because strong forces hold nucleons together, the nucleus is at a lower energy than the individual components themselves. So when you separate out those nucleons and make the nucleus, combine the separate nucleons to make your nucleus, you're going to release a lot of energy, a lot especially in comparison to a chemical reaction. So nuclear energy is going to be produced at the expense of mass, implying that the nucleus mass is less than each individual's added up together. Nuclear binding energy is the energy that is emitted when nucleons come together. So it's the energy that would be needed to break a nucleus apart. If you look at this diagram here, down here at the end, it says the repulsions are going to become more significant because the energy is going to decrease. This bar that they're pointing to here, the region of very stable nuclides, any levels beyond this, because the nucleus, this levels off beyond this because the nucleus is too large for any extra added nucleons to increase the overall attraction for other particles. So you're going to have this leveling off in the stabilizing part. Beyond mass 209, there's no stable nuclide that will exist. And just kind of another general fact here, the isotopes that have a high binding energy are going to be more stable. Iron 56 is going to be the most stable nucleus, which just means that it's going to hold itself more tightly together. The more energy that gets released in the process, the more stable the products are going to be. And then the band of stability looks like this. You're plotting, it's called the NZ ratio. These are the N values, your number of neutrons, and then across here are the number of protons, and this is your Z value. Anything below this is going to be 1, and anything above this is 1.5. So the area, the band of the stability refers to the area on this graph of the neutrons and proton numbers where the stable nuclei are going to lie. And then nuclei are going to be more stable if they have more neutrons, or at least equal neutrons to protons. There are a couple exceptions. The smallest nuclei, hydrogen 1 and helium 3, those are exceptions to that rule. Nuclei are going to be more stable if they don't have too many or too few neutrons. So basically the ratio needs to fall between that 1 and 1.5 on the band of stability. So essentially as the nuclei increases in size, so does the ratio. And if nuclei are going to be more stable if they have even numbers of nucleons. or if they have magic numbers of protons or neutrons, which are listed here, 2, 8, 20, 28, 50, 82, or 126. Those are magic numbers, and those are going to be more stable. And then the last one is if they are not a neighboring isobar. So if you've got two neighboring isobars, at least one of those is going to be unstable.